Hello and welcome to the seventh lecture on quantum computing. Today we'll look into some more of the fundamentals needed for designing algorithms and also repeat some of the things that we did last time, just to keep it in our minds. We talked about, so over the last lectures, we talked about how you represent quantum gates with matrices. We know in the meanwhile pretty well how to do that, but it will often be useful to adopt a graphical representation. And that's how we concluded our last week's lecture. And this is done as follows. So you see here in a graphical representation an input register consisting of n qubits and an output register also consisting of n qubits. And in between you see a unitary transformation that is applied on all of the input qubits, producing a certain output state. So this is given here on the left as well. Here you have the unitary that you apply to the input state I, resulting in the state Q. Each input line and output line represents the evolution of one qubit. Okay, so that doesn't necessarily mean you have to apply one qubit transformations only, or you can only apply one qubit transformations. It means just that you follow different lines for different qubits. And you can, of course, apply multi-qubit transformations, so execute a transformation on multiple qubits at once. Here's another example on the bottom where we have the NOT gate, so which is given by X, and you see again an input state, apply the X transformation and resulting or producing the state Q. So if we look at that in more detail here, just to remind you, we have the input state I here. We apply the NOT gate twice. So after application or first application of the NOT gate, we end up with the state I prime, which is here on the bottom. It's given by I prime is application of NOT to I. So it means you do the NOT application here. You see the two amplitudes, A sub 0, A sub 1, and it flips the amplitudes. And the state Q is produced by applying the NOT gate to the state I prime, which again flips the amplitudes. Okay, so this is what we expect from a double NOT application. And also if you execute that multiplication here, down here, so the double NOT, you end up with the identity, which makes sense because in the end we end up with the original state. And since we want to have reversible transformations, we want to have unitary transformations, this is one that fulfills all the criteria. We have looked at other examples. So for example, the controlled NOT gate, but we're not limited to the controlled NOT, so we can control other gates as well, which means we need a control bit, or at least one control bit. So remember that hopefully, for example, has two control bits, but we need at least one control bit, and graphically represented by that dot here on the bottom. So where this first qubit here, this line represents the control bit, and only if it is 1, you apply, or the Z gate is applied to the second qubit. Right? So the state of the first one is not changed at all, just checked if it is 1 or 0, and if it is 1, we apply the Z transformation resulting in that new state Q here. The controlled Z is given by that matrix, and so if you look at it, so here on the bottom, you can see the Z part, and here the control part, so it leaves that one alone. Okay, so it means it doesn't change that control bit. So then we consider the circuit, this one here on the bottom, this one, sorry, and here you have two controlled gates. So first one is input state I again, then you apply the controlled Z gate resulting in the state I prime, and then after that you apply the controlled NOT gate resulting in the state Q. And if we look at that in the first one here, then you see that the order is reversed. So here the Z gate in the direction that you read comes before the controlled NOT gate. And here, if you read it from left to the right, you see the controlled NOT gate before the Z gate. And this is very important because here what you want to do, of course, is apply the controlled Z gate before the controlled NOT gate. So the sequence here matters, okay? So the order matters. And you can, of course, again, create one transformation out of these two. So it's both of them are 2-qubit operations. So there is no need to do a tensor product because our space doesn't become bigger. So we just do the multiplication again and produce that state, that transformation here, which is the controlled not controlled Z transformation that we see here and executed here. Let's look at a slightly more complicated example, because in the algorithms that we will study next, we'll need to be able to analyze circuits containing both 1 and 2 qubit input gates. Okay, so it's a little more complicated, but still not too complicated. Now, if we look at that circuit here in the slide, and we see we have an input register again. This time it holds 2 qubits. We start in a well-defined state, something that we understand. So we have 4 possible input states for the register I. Then we apply the Hadamard transformation, but only to the first one. We leave the second one alone. Nothing happens to the second one until we're here at the controlled NOT operation. So say leaving the second one alone, as you remember, means applying identity to it. So what we want to do now is construct a 2-qubit gate that does exactly the job. So it applies the Hadamard transformation to the first one, and it leaves the second one alone. And we call this transformation M, for the lack of a better name right now. And it's also given here. So the state I prime is produced by applying the transformation M to the input state I. And now let's look at how to construct the transformation M. So we have 4 possible input states for 2 qubits, which are 0, 0 to start with. So and if we apply that transformation, so the Hadamard transformation to the first qubit here. The second one we leave alone, so we apply the Hadamard to the first one, which then gives us 1 over the square root of 2, 0 plus 1. And so we still have the second qubit, which remains in the state 0 for now, which gives us as a final result, so it's the same, 0, 0 plus 1, 0. Now, the second one that we look at is the state 0, 1. Again, we apply the Hadamard transformation to the first one, which gives us 0 plus 1. We still have our second qubit here with 1, giving us the final state 0, 1. Sorry. 0, 1 plus 1, 1. The third possible input state that we have, that we can start with, is 1, 0. So what this gives us, it's the same Hadamard transformation. What this gives us is the same superposition state, or actually not the same superposition state, because there's a different relative phase here. So remember, applying the Hadamard to 0 gives us a positive relative phase, applying it to 1 gives us a negative relative phase. So again, a superposition on the state 0 here. Sorry. Producing the final result, 1 over the square root of 2. And here, I multiply that out, 0, 0 minus 1, 0. And now the last one is the state 1, 1. Again, we apply the Hadamard transformation. We get 0 minus 1 here. And then we have our second qubit here, still giving us the final result, 1 over the square root of 2, 0, 1 minus 1, 1. Very good. So now that we have these four possible outcomes for the transformation M, we also want to understand how we can construct the matrix. Okay, so remember what we did before is we take um, we take our first input state, which is given by 0, 0, and we take our first target state, which is given by 1 over the square root of 2, and we do the bra states now. So we have 0, 0 plus 1, 0. We multiply that out and get a result of this. So it's 1 over the square root of 2, 0, 0, 0, 0 plus 0, 0, 1, 0. So if we multiply that out to create the outer products in matrix form, let's also look at that. Then for this case, we end up with 1 over the square root of 2. So we do the first one, 0, 0, which is given by 1, 0, 0, 0, and multiply that with 1, 0, 0, 0, plus the second one, which is given by, oops, don't know why it does that sometimes, which is given by 1, 0, 0, 0 times 0, 0, 1, 0. Which gives us 1, 0, 0, 0. Everything else zeros, plus 0, 0, 1, 0. Everything else zeros. So much for the first one. Now let's look at the second one, which is given by 0, 1. The target state is given by 1 over the square root of 2. And again, we look at the bras here, is 0, 1 plus 1, 1. We multiply that out. We get 1 over the square root of 2 over 2 of 2. Then we have 0, 1, 0, 1 plus 0, 1, 1, 1. All right. And if we look at these outer products, as we just did before, we will get as a result 1 over the square root of 2. Then looking at the first one, 0, 1 is 0, 1, 0, 0 times 0, 1, 0, 0 plus 0, 1, 0, 0 times 0, 0, 0, 1. Okay, we multiply that out. We will have 1 over the square root of 2. For the first one, we have all zeros in the first row. We have a 1 here. Everything else 0. Plus, for the second one, all zeros in the first row. We have a 1 here in the second row. All zeros in the remaining matrix. Okay. And it's analogous for the other ones, but just to be complete here, let's also do the remainder. So we start with 1, 0, and the target state in that case, again looking at the brass, is 0, 0 minus 1, 0, giving us 1, 0, 0, 0 minus 1, 0, and 1, 0. Okay. So then again, looking at the outer products here, we have 1 over the square root of 2, and we look at 1, 0, which is given by 0, 0, 1, 0, 0, 0, which is given by 1, 0, 0, 0, and we have a negative phase here, minus 0, 0, 1, 0, 0, 0, 1, 0, giving us so for the first one, all zeros in the first row, all zeros in the second row, we get a 1 here in the third row, and we get all zeros in the fourth row. Okay, plus we get all zeros in the first row, we get all zeros in the second row, we get all zeros here, here we have a negative 1, and we get all zeros in the fourth row. Okay, so that's the third one. And now let's look at the last one, starting with our input state, which is 1, 1 in that case, taking our target state, again looking at the ket, which is 0, 1, minus 1, 1, leaving us with 1 over the square root of 2, 1, 1, 0, 1, minus 1, 1, and 1, 1. Giving us the our products. It looks like that is 1 over the square root of 2. We look at 1, 1 here, so meaning we have the state 0, 0, 0, 1 times 0, 1, meaning 0, 1, 0, 0, minus 1, 1, times 1, 1. If we multiply that out, then we get, for the first one, all zeros in the first row, all zeros in the second one, all zeros in the third, and we get 0, 1, 0, 0 in the fourth. And then we have, for the second one here, all zeros in the first row. We have all zeros in the second row. We have all zeros in the third one, and we have a -1 here. Okay, so now we did that. The last thing that we need to do, if we look at these four now, is we have to add these up. Giving us the final transformation M. So if we add that up, quickly look at that again. Okay, if we add that up, our final transformation will be 1, 0, 0, 1, 0, 0, 1, 0, 1, 1, 0, -1, 0, 0, 1, 0, -1. All right, so that's how you get to the transformation M. Now, if we go back to the slides, here you can also see the result, which is identical, hopefully identical to what we just produced. And now taking that M transformation, we can move on and take the controlled NOT transformation that we also already know and use the controlled NOT operation and multiply it with the transformation M to create a new transformation, which is this one here. So which would give you a combined controlled NOT M on the state I, producing the output state. And you see here you have different output states based on input states. So it's not what we just had when we only produced M. So this is also already the controlled NOT applied after executing M. And you can see the control bit. So if we look at that state, for example, here, if we look at the previous slide, this one here, then we see we had 1, 0 before, and now it created or changed the second bit based on the control bit, the second half of the state to 1, 1. And the same for the other states. And again, we produced that entangled state. So these are the Bell states, the maximally entangled states for the first one. And again, just a reminder, different way of writing this is again 1 over the square root of 2, 0, 0, 1 over the square root of 2. And Bell states are created. So these states are the maximally entangled states. It's not possible to decompose them into single qubit states or construct these states out of single qubit states. So you always need the controlled NOT operation and the Hadamard before. We did that quiz. I hope you didn't have any problems and could solve that. So if you had problems, please, as always, reach out to me and we'll go through this together. Now, one other thing that we want to look at today is the no cloning theorem. The no cloning theorem just says that you cannot clone a quantum state. And we will look at both quantum and classical probabilistic states to understand if that's also true for classical states. So maybe there is a connection here that is not as obvious if we just think about cloning quantum states. So we're not talking about cloning DNA. It's one of the earlier results in quantum information, so which just says if you have the state of one qubit, you cannot copy it. So you cannot copy the state of one qubit into another qubit. And why this is not possible, we will try to understand now. So let us assume we have in our lab a qubit in an unknown quantum state. So we know it's in a superposition state here, the state psi, given by alpha 0 plus beta 1, but we don't know the amplitude. So we know it's in a superposition, so therefore it's an unknown state. So we don't know if it's equally weighted or anything else. We don't know about it, and we can say maybe some external referee knows about this state, so knows more than we do. And so now the question is if it's possible to design a machine which for all possible states psi, so meaning all possible probability amplitudes that we see here, is it possible that we construct a unitary that allows us to copy this state, so in something that looks like that? So hence cloning the state, so create a copy of this state in another qubit. Is that possible? So let's check. So let's again start with a very well-defined and understood state for our copy qubit here. So we have state 0, and the intention now is that we take this original state psi and we copy it into that second one, so that in the end we get this one. We have copy of the psi state. So, and for this, we now assume, since we're dealing with unitary transformations here in quantum computing, we assume such a unitary exists. So a unitary that allows us to clone that state. And that unitary for these two states, so saying we have the state 0 here, so we apply the unitary to the state 0, it would give us 0, 0 here, and assuming we apply that unitary here, then it would give us 1, 1, okay? So that's what we want to have. We want to have a copy of the first qubit in the second one. So if this is true, then by the linearity of quantum theory, what would give us, what would be the result of that state here on the bottom? So if we have a superposition state, and we want to clone that superposition state into our second qubit here. So let's see what happens if we try. So by linearity of quantum theory, it says if we have our superposition state, and we have that second qubit here, then this is the same state as executing that tensor product here. Okay, so you just multiplied that state 0 in, but which is certainly not equal to this one here, which is two qubits in superposition in that case. So which is what we would require if this were a cloning unitary. So therefore, we must have a contradiction here. No such a unitary can exist. This is a very important result. So just let's go over it again. So the linearity of quantum theory says that if we execute that transformation here, they execute the tensor product here. So multiply this one, 0 times 0, 1 times 1, and then we clone each of these. So 0 would go to 0, and 1 would go to 1. This would be the result, assuming such a unitary exists, right? So what we did here is superposition, execute a tensor product, then we copied the first qubit into the second one for each. But now, if we look at this slightly differently from a different angle, which is just taking the superposition state, not executing the tensor product, and saying this is what we will clone into the second qubit, then this would be the result. But this is totally different to the first one. They are not equal. So therefore, by arguments of linearity, we could show that such a unitary transformation does not exist. But is that also true for classical transformations? So we've shown that for cloning theory for qubits and for unitary transformations, but now let's look at the classical system. So now if we look at this from a classical perspective, so remember when we talked about the postulates of quantum physics, quantum mechanics, then so we had these four postulates and we compared classical to quantum computers. So for the quantum computers, we just took qubits, and for the classical one, we took classical probabilistic systems. So we had systems that used classical probabilistic states. So for ending up in a state 1 in a two-state system here, you see the probability p, and for ending up in a state 2, you see the probability 1 minus p here. So now is it possible to turn this into two copies of the probability distribution? So for all possible probabilities of p, that's the question that we ask ourselves. Here, at first we may think, of course, we can do that. We just copy the bits. But if we take this state here, for example, and copy the first bit into the second, the probability distribution that we get is, so p times 1 gives us p, then we have p times 0, 0, and we have 1 minus p, and again 0 here, which is totally different from what we would expect. So therefore, we have used the same argument here to show that even with classical machines, there is no way to clone the probability distribution. Okay. So, and why we did that is it's very important that we always challenge ourselves to distinguish the difference between classical and quantum information processing devices. That's very important. Sometimes we may make assumptions that do not turn out to be true. So anytime you just make an assumption, better verify. So, and then be sure. Okay, that's very important. Now, the next thing that we look at are measurement gates and the Born rule. And we talked about this briefly before, the measurement and what the Born rule is. So the Born rule is just we need to square the probability amplitudes to get the result. And measurement means it's a destructive operation. So anytime we do a measurement, we lose all that rich information in the superposition state. So it's a very special operation in quantum computing, and we need to look at it a little closer, which we're going to do now. So to give the state of a classical bit requires one bit of information, whether the classical bit is 0 or 1. But we need arbitrarily many bits of information to specify an arbitrarily high degree of precision in a quantum bit. Since we remember, if it's in a superposition, we have two complex numbers, alpha and beta, which are subject only to the normalization constraint that specify the state of that qubit. So therefore, the conclusion can be that qubits have a richer set of states compared to classical bits, and a richer set of transformations can be used to act on them. And therefore, quantum computing is more powerful than classical computing. There's a problem though. So as you remember, measurement is a destructive operation. So if we look at classical bits again, looking at a classical bit doesn't harm the bit. So even if I have a string of bits and I execute a computation on this string of bits, manipulate that string of bits, at any time I can interrupt that computation, read out the intermediate result, and continue. Looking, therefore, is not disruptive. Whatever looking means, it depends on the implementation. If we want to determine the state of a qubit, then let's say we have n qubits in a superposition, there is no way to extract the information encoded in these amplitudes. So the amplitudes associated with each possible state. Anytime I do that, I make a readout, so I measure the system, it will collapse. So we talk about decoherence here. And that means it will collapse into one of its eigenstates. So in the computational basis, if you have a two-qubit system, then remember it has 4 orthogonal vectors. So assume you have one probability amplitude associated with each of these possible states. Once you look at it, 3 of them will be gone and it will collapse to one of these final states, one of the states. And the state of n qubits is not associated with any property of these qubits as it is for classical bits. So in short, if you look at it, you lose information. So you better only look at the bit or at the system once you're sure you're done with your computation. So that's what we call making a measurement or measuring the system. And yeah, as we said, for one qubit system, that's 0, 1, 2 qubits, one of these 4 vectors, for 3 qubits, one of the 8 vectors, and so on. So the probability of getting a specific result, so in that case, we have this example 0, 0, 1, 0, 1 here, is given by the squared magnitude of the amplitude, as we remember from the previous lectures. So you have these complex numbers, you do squared magnitude, and so for each of the 2 to the power of n computational basis states, you have one of these amplitudes. And remember, the quantum computer is a probabilistic system, so even if you run an algorithm and you do everything right, you still may get a result that's not the solution to your problem, not the desired solution. You may still get a solution that's not optimal or even far from optimal. That's because it is a probabilistic system. So, the artistry in quantum computing is really to shift the probability amplitude such that once you look at the system, the state, the desired state, is what you get most probably. Okay. So if the state of n qubits is encoded like we have it here, with so in that case, on the bottom we have 5 qubits. Then for the first one, for 0, 0, 0, 0, you have a probability amplitude, same for 0, 0, 0, 1, and so on. And remember, you do the squared magnitude. So, and here, for complex numbers, if we say my complex number is alpha sub x, then that's how you do the squaring, right? So you take the complex conjugate multiplied by the original. And the measurement is done by a piece of hardware, so depending on the implementation of the quantum computer. And very often in our algorithms, we depict it. And there are different ways, so different authors use different ways of depicting it. One way, as you see here, is by indicating it with these fancy lines here, so doing a measurement. And here you see at the beginning you have probability amplitudes associated, and then we end up with a definite state. No probability amplitudes anymore. 2 to the power of n, that's just the number of computational basis states that we have. So remember, if you have 2 possible states, you have 2 bits, you have 4 possible states, 4 possible configurations that the system can assume. If you have 3, it's 8, and so on. And also remember, that's one of the crucial properties of a quantum computer. Anytime you add a bit, so if you have perfect quantum bits here, anytime you add a bit, you double the computational power. There's more to that. So specifically, remember physical and logical qubits. If you have qubits that are not perfect physically, then you may need more physical qubits to represent one logical qubit. And therefore, then this is not true. But in theory, so we're talking about perfect quantum computers here. Theory, if you have perfect bits, then you add 1 bit and you double the computational power. A measurement cannot be undone. In contrast to the action of the unitary gates on a state. So remember, all the operations that we looked at are reversible. So apply it twice and you get the original result. But there is no way to reconstruct psi, the quantum state, so holding a superposition of possible basis states from one measured basis state. So the measurement indicates some pre-existing property, such as weight. However, it just refers to reading the display of a measurement gate whose action is specified by the Born rule. And there are different ways to interpret it, even goes into philosophy, or you could say there is no physical reality until you look at a system. So I prefer to say too that it's just a distribution of possible states, and we look at the system, and then once we do that looking, so measure the system, then we get our physical reality, our definite state. For a single qubit, if the qubit is in a superposition, as we have here, psi given by alpha sub 0 with the state 0 plus alpha sub 1 with the state 1, And the probability for measuring 0, as we had it before, is alpha sub 0 squared. So we'll do the alpha sub 0 times its complex conjugate. And same for the state 1. And the n-qubit measurements are carried out by applying 1-qubit gates to each of the n qubits. Okay. The second aspect of action of measurement gates, besides displaying an n-bit integer, so that's the result that you get, an n-bit integer, after a measurement of n qubits, the display shows integer x, then one must associate with the qubits emerging from that measurement gate the classical basis state x sub n. That's just what we said before. So all the rich information encoded in your superposition, that is gone, but you will be left with one definite state. That's what it is. And to summarize that, for the Born rule, that's what's called the Born rule. So after a measurement resulting in a definite state, such as this one here, we don't talk about psi anymore, this superposition state that we had in the beginning before we did our measurement. It is this state, so characterized by that state vector. And it's referred to as collapse, reduction, decoherence. So you hear multiple different ways of describing that. So the state of n qubits is just an abstract symbol used via the Born rule to calculate the probabilities of measurement outcomes. And the whole artistry, as we already mentioned a couple of times in quantum computing, is or comprises to construct a superposition by unitary transformations in which most of the amplitudes alpha sub x are close to 0, extremely close to, so they will never be 0 because we're talking about a probabilistic system here, with useful information being carried by any of the values of x that have an appreciable probability of being indicated by measurement. So that means the algorithm that you implement, in that algorithm, you must make sure that the measurement outcome with high probability gives you the solution to your problem or lets you learn something about your problem. Okay, and this is done by the transformations. So a state such as psi given by a superposition of 0 and 1 here with two probability amplitudes does not mean that the actual state of psi is 0 with probability alpha sub 0 or 1 with probability alpha sub 1. The action of the test itself may play a role in the outcome. So such an assertion goes beyond this rule, the assertion that we have these probabilities associated with each of the possible outcome. So such an assertion goes beyond the rule, which only asserts that if one subject a qubit in the state psi to a test, this measurement that we talked about, then the outcome of the test will be 0 or 1 with those probabilities. The post-measurement state of the qubit can be taken 0 or 1. That does not mean that prior to the test, the qubit has already carried the value revealed by that test or by that measurement in that case, and was already described by the classical basis state, because among other possibilities, the action of the test itself, that's the important phrase here, the action of the test itself may play a role in bringing forth the outcome. So the measurement itself may influence the state. It is not just a collapse of the superposition, it may still change the probability amplitudes. And an example is the Hadamard transformation is linear and norm preserving, thus unitary, and a quantum computer can apply it to the state of a qubit. So it is a 1 qubit gate in that case, but can generalize to n qubits. But since the states 0 and 1 form a basis, this determines the action of Hadamard gate on 1 qubit state. Because it's linear and norm preserving, it's unitary, it's therefore the kind of operation a quantum computer can apply to the state of a 1 qubit gate. Okay. According to the Born rule, if we look at this a little closer, the state phi in that case, superposition state is given by 1/2 of the probability of a state being in 0, 1/2 being in 1, and the application of the Hadamard transformation on that state always results in a definite state, 0. Okay, so that's the state. We know we started with 0 when we look at this superposition on top here, because we have a positive phase here, a relative phase. And if you apply it again, it will collapse back into the definite state 0. So what if the state psi were indeed either in the state 0 with probability 1/2 or 1 with probability 1/2? In either case, the subsequent action of H would produce a state, either 1 over the square root of 2, 0 plus 1, or 1 over the square root of 2, 0 minus 1, as we have learned previously already. And that other measurement would yield 0 or 1 with equal probability. So the Hadamard transformation per se gives you an equal probability distribution of your bits of your superposition state applied to a definite input state. So which contradicts the fact that we just extracted directly from applying, if we look at that form before, applying our Hadamard transformation, applying our Hadamard transformation to that state here gives us 0, because it's invariably 0. So a qubit cannot be viewed as being either in the state 0 or 1 with certain probabilities, as it is something quite different. So although the qubit reveals only 0 and 1 when queried with a measurement gate, or when measured, in short, prior to the query is not, in general, either 0 or 1, but an overlapping state called the superposition state that we have always been talking about so far, in the form of psi alpha sub 0, alpha sub 1, or represented by a probability distribution. And such a superposition state, so that's we have to wrap our mind around that, is as natural and irreducible of a qubit as 0 and 1 are. Now, if the states are restricted to computational basis states, then the process of measurement is just like the classical process of, you could call it learning the value of x without altering the state. So thus a quantum computer can be made to simulate a reversible classical computer by allowing only computational basis states as input and using only unitary gates, such that the computational basis states are transformed into computational basis states. And the Born rule relating the amplitudes alpha sub x in the expansion that we saw before, where we had our superposition state. So let me quickly go back. This expansion here. So if we keep that in mind. So relating the amplitudes in the expansion that we just saw of a general n-qubit state psi to the probabilities of measuring x is often stated in terms of inner products or projection operators, as we just saw before, right? So we did the projection operator, which for 0 and 1 always projects on the state 0 and 1, which you can get by doing the outer product, and the probability of a measurement giving the result that we see here. Is given by this rule here on the right. Okay, so you have that definite state, one of the outcome states, and here you have the state psi. You take the inner product and you get the probability. So inner product, square that, and you get the probability of the state collapsing into that definite state here. In terms of projection operators, we can do the very same. You remember the projection operator. If we just, if we write that down again for the state 0, then the projection operator is given by, which is this one here, okay? Never mind that small dot here. So it's the 2D matrix that we see here. And the probability of measurement giving this result is given by this one or this one here. Okay. So if we look at p sub psi here, it's the projection operator on that state, psi itself. And if we look at p sub x here, that's the projection operator on the state x. So in case of our zero state, it would be that one here, the projection operator onto the state zero. So if we now look at a 2-qubit system and we only want to measure the first qubit, then we have a subspace decomposition of given S sub 1 and S sub 2, where we look at the subspace S sub 1 as containing all the states where we measure 0 for the first qubit. And the same for the second one. We look at S sub 2 containing all the states where we measure 1 for the first qubit. And an arbitrary 2-qubit state, as we have seen before a couple times already, is given by the 4 possible states associated with 4 possible probability amplitudes. And once it's measured, because we have 2 different subspaces here, we have this normalization factor here, and probability of measuring, so psi sub 1, probability of measuring psi sub 2 here. So for psi sub 1, we look at the states that have a 0 in the first qubit. For psi sub 2, we look at the states that have a 1 in the first qubit. And we apply that normalization factor here. For the state psi sub 1, we have the normalization factor C sub 1 containing the squared probability amplitudes for both possible states containing 0 in the first qubit. And the same we have here for C sub 2, where we have the probability amplitudes for both states that can contain a 1 in the first qubit once we measure the system. So the measurement results in that state psi sub 1 with a probability, so the squared normalization factor here, of C sub 1 squared, which is the squared probability amplitudes for the 0 states and the squared probability amplitudes for the 1 states given by C sub 2 squared. So for measuring psi sub 2, okay? So the generalized Born rule, if we now look at that, is a stronger version of the Born rule. It applies when a single one of n plus 1 qubit is measured. So before we looked at 2 qubits, now we look at n plus 1 and measure only 1 qubit. So we apply a 1 qubit measurement gate, and any state of n plus 1 qubits can be represented in the form that we see here with the probability amplitudes alpha 0 sub 0 squared and alpha sub 1 squared, so subject to the normalization condition again. Okay, so if we're talking about subspaces again here, if we now look at this state here where we have alpha sub 0 for the 0 subspace, so with psi 0 here, and alpha sub 1 with the 1 subspace, and psi 1 here, this one should be squared. Then for phi sub 0 sub n and phi sub 1 sub n, if we look at these ones, they're normalized but may not be orthogonal, which follows from the very general form that we see here on the bottom, where we have our probability amplitudes gamma of x associated with each of the possible x sub n plus 1 states here, subject to the normalization condition as always. Now, the states psi sub 0 sub n and psi sub 1 sub n are given by here on top for measuring a very specific state. So this one, state x sub n, so which can be n qubits, is what it means. We have this probability amplitude gamma of x associated with that certain state, and then we have the state psi sub 1 here, and so here too we have 1 over alpha sub 1 and the probability for the 2 to the power of n plus x states. And if we look at the probability amplitude, the probability, so for the first one, for a, so 0 squared, we look at the gamma of x squared. And if we look at the second one, so where we have the remainder of the states, so a sub 1 squared, then it's given by the probabilities for all the 2 to the power of n plus x states squared. Okay, and together, as just said before, they again sum to unity. So it asserts that if a single qubit is measured out of a state of an n plus 1 qubit state, a 1 qubit measurement gate will indicate 0 or 1 with probability of alpha squared. Okay, after that, the n plus 1 qubit state is the product state of this definite state that we measured and the other qubits in superposition. So if you remember, before we looked at very simple systems where we had definite states and 1 qubit in superposition. So when we created entanglement, then we applied the Hadamard transformation only to the first one, and we still had a definite state in the second qubit, which was 0 or 1. And so this is nothing to do with measurement, but it's a very similar situation where we have one definite state and a product state with a superposition state. Okay, so if qubits are unentangled, the measurement equals the standard Born rule measurement. So unmeasured qubits play no rule at all. It's different with entangled qubits though, because we learned you cannot look at an entangled qubit system as still single qubit systems. So if you do something to one qubit, it will affect the state of the others if those states, if those qubits are entangled. So here we can apply a measurement n times to successive 1 qubits. So if that's given by psi sub n, then we will get for all the possible states, again, the probability squared for that specific, a very specific state. And the final state of these n qubits is x, which is one definite state. So it's an n-bit integer given by the readings on the n 1 qubit measurement gates with the probability, again, alpha sub x squared. So you will, if you execute a measurement on all the qubits in sequence, then again, you will end up with a one definite state, a multi-qubit definite state. Here we see a 4-qubit measurement gate constructed out of 4 1-qubit measurement gates, and x has the binary expansion, in that case x sub 3, x sub 2, x sub 1, x sub 0, here indicated here on the top. Okay. So an even more generalized Born rule is the general state of an n plus n qubits can be written as psi sub n plus n. Then we again have our definite states having n qubits associated with a probability amplitude alpha sub x. We have 2 to the power of n possible states, so that's what we run over here. And we have our other state, so the second part of the state with psi sub x sub n here. Okay. So again, we have the alpha amplitude squared to unity, so the probability to unity, and states psi sub x sub n are normalized but may not be orthogonal. And applying the rule, the Born rule that we just learned about m times in an n plus n qubit state, so the m qubits on the left are measured with the probability of alpha squared. The result will be x after measurement in the state of m plus n qubits will be x sub m, and still our states psi sub x sub n. Anytime I say alpha squared here, it's just laziness that I don't say the absolute value or say the modulus squared. But I trust you know what I mean if you look at the bars here. Okay. Now for that one, we want to go through a quiz. So I have a couple of questions here again that you can work through, and I attached the solutions on the next slide. So please try that out. And again, if you have questions, as always, please feel free to reach out to me and we'll discuss in detail. Now, let us briefly talk about measurement gates and state preparation. We heard a couple of times already that we have to start our computation in a well-defined state. So your input register, our input register, has to be in a state that we understand well in order to execute a reasonable computation. But there is no way to determine the state of a given collection of qubits. So how do we do that? What we do is we measure. So we measure our input registers or measure our state of n qubits with an n qubit measurement gate. And for each of the qubits that registered 1, we apply the NOT operation. So leaving us with a state of all zeros. So we have an n qubit state, all in zeros. So that's then a well-defined state that we can use to start our computation. So we remember we have two roles of measurement then. We have the state preparation, which we do at the very beginning, before we start the evolution of our circuit, before we do our computation, and we measure the system if we want to extract the digital output after the computational action that we perform. So the role of measurement gates in state preparation follows from the Born rule. If qubits to be prepared already have a state on their own, which may not be known to the user of the quantum computer, and the generalized Born rule if qubits share an entangled state, again, which may not be known. So it's impossible to deduce from Born rules, from each of the ones that we looked at, that measurement gates allow preparation of states for qubits with unknown past history. So such cases require the use of measurement gates as an extension of the Born rules. Other ways to get a state, an all zero state in physical realizations of qubits is, for example, so if we have atoms and we use the lowest energy state, the ground state, it's called, of that atom as the zero state, then we can do it by cooling down the atoms. So the lower the temperature, the lower the energy states. And the state 1 can be, for example, the next lowest energy, so the first excited state. So if we cool that system down, then we will also have a configuration that we can use as a starting state. By the way, for superconducting qubits, we have to cool the system down anyways, because we're dealing with superconductors. So remember, I think at the beginning I mentioned different ways of implementing quantum computers. One of these ways would be having rings of metal. And this is a very simplified representation. So we have rings of metal. This is one qubit that you see here, a superconductor. So we cool it down to 15, 20 millikelvin, something around that temperature. So it's very close to absolute zero, colder than space. In space, we're dealing with 2.7 Kelvin approximately. And so we induce current in both directions, which in turn creates two magnetic fields, one up and one down. And this is the magnetic spin qubit that we're dealing with. So from a conceptual point of view, state preparation by the use of measurement gates is the simplest way to do it. And the acceptable physical candidate for a qubit must be a system for which measurement gates are readily available. So which we don't only need for state preparation, but also for extracting a useful result. Okay, so much to measurement. Now let's look at constructing arbitrary 1 and 2 qubit states. So constructing circuits out of 1 and 2 qubit gates that produce final states capable of revealing useful information when measured is the goal here. So we really want to stack together a series of gates that incorporate our algorithm. And we want to use 1 qubit gates when possible and 2 qubit gates if needed. So we want to interfere as little as possible with our qubits. So that's very important because these systems are very sensitive to interactions. So be that influence from the environment, be that their own irrelevant properties, be that running or the execution of unitaries, of transformations. So 1-qubit gates are comparatively easy to construct, and 2-qubit gates are not just tensor products. We'll have a closer look at. So much to measurement. Now let us construct arbitrary 1 and 2-qubit states. So we talked about this before. The art of quantum computing is constructing a sequence of gates that will change the probability amplitudes of our system such that once I look at it, once I measure it, I get some meaningful results, something that helps me to solve my problem or even solve my problem. So we construct circuits out of 1 and 2-qubit gates that produce final states capable of revealing useful information when measured. We do 1-qubit gates whenever possible and 2-qubit gates whenever needed. So remember we talked about that at the beginning, so we want to interfere as little as possible with that system. And there is, of course, the interference or influence of the environment. There are the system's own irrelevant properties, and there are also the operations that we execute on the qubits, meaning the unitaries. So these are interactions, and we want to minimize these on many qubits. 1-qubit gates are comparatively easy to construct, and we also have 2-qubit gates that are not just tensor products. Okay, so that's also important. So the attention so far has strongly focused on C sub ij and gates that can be constructed from C sub ij with 1-qubit unitaries. So remember, C sub ij is the controlled NOT gate where we take the first, usually the standard version, take the first qubit as control gate, the second as target, but it can also be flipped around. So vice versa, where we have the second qubit as control bit and the first one as target bit. So all circuits which we're going to examine are combinations of 1-qubit gates and 2-qubit controlled NOT gates. Controlled NOT gates are difficult to make. Their number should be minimized. So let psi be any 1-qubit state and phi be the orthogonal state unique to within an overall phase satisfying this condition here. Okay, the inner product gives 0. Which means they're orthogonal to each other. As 0 and 1 are linearly independent, there is a unique linear transformation taking them into psi and phi. So since phi and psi and phi are orthonormal, so remember orthogonal and unit length here, that's what orthonormal means. This transformation preserves the norm, so it is a unitary transformation, U. For any psi, there is a 1-qubit unitary gate taking the state 0 into psi, which is just the gate state psi, as we saw before, unitary applied to the definite state. That gives us the state psi, whatever that unitary is. So in an unentangled 2-qubit state, which is the product of two 1-qubit states, so indifference to the entangled 2-qubit state, can be constructed out of 0, 0, so that starting state here, by the application of 1-qubit unitaries to each of the qubits. So we have our well-defined starting state here and apply 1-qubit unitaries to each of the qubit. A general 2-qubit state is entangled though, so and that makes it more difficult. So its production requires a 2-qubit gate that is not just a tensor product of 1-qubit unitaries. Okay, because remember, also when we look at that state, we cannot deconstruct it into single qubit states, such that if you execute a tensor product between these two, you get the entangled state. That's not possible. And we saw that before. It can be done with a single controlled NOT gate combined with 1-qubit unitaries. The general 2-qubit state we see here, we saw that quite some times before already, so is given by psi here with the 4 probability amplitudes that we already know of, and is of the form 0 for the first one and plus 1 tensor product phi for the second one. And for 0, remember that's the states, so the 0 states where we have the first qubit being 0, and the 1 state here is where we have the second qubit, the first qubit being 1. Okay, now let us apply a unitary, so U with a tensor product of 1, so here this is the identity again, to the state psi, where U is a linear transformation whose action on a computational basis is of the form, so U applied to 0 gives us A with the state 0 plus B with the state 1, and U applied to the state 1 gives us minus B star with 0 and plus A star 1. Okay, so and for both we have the squared amplitudes again, they must sum to unity. So if we now apply that, so just take U of the state 0 here, you look at that one, with the state psi, then it's the same as we had on the previous slide here with 0 and the state psi. So that's what we do here. And for 1, the state phi, which is what we had in the previous slide here, 1 with the state phi. Okay, giving us this nice result here with psi prime and phi prime, where we just summarize phi prime as A with phi minus B star phi as A psi minus B star phi, and phi prime with B psi minus A star phi. Okay, A and B should be chosen in order to make psi and phi prime, so psi prime and phi prime orthogonal to each other. And here we can check the inner product, and if we see that these states, so phi and psi, doesn't give us 0, then setting phi prime and so the inner product of phi prime to psi prime to 0 gives a quadratic equation for A over B star with two complex solutions. And if A in either of these that we see here is any non-zero complex number, then either solution determines B, which with A gives a 1 qubit unitary for which this is true. So we take our initial transformation U and tensor product with the identity plus applied on psi. So if we make sure of what we just said before, then psi prime and phi prime are orthogonal. If the inner product of phi and psi equals 0, then psi is given by 0 times psi and 1 times phi, and is already of this form with U equals 1. So we now may pick two positive real numbers, lambda and mu, such that psi double prime equals psi over lambda and phi double prime equals phi over mu, which are unit vectors making psi double prime and phi double prime an orthonormal pair. And they are therefore related to 0 and 1 by a new unitary transformation V. So, which we can say psi double prime is given by V applied on the state 0, and phi double prime is applied by is given by V applied to 1. And now, if we do our initial transformation, so if we look at that again, so U times 1, so the identity applied on the state psi, then the result that we discussed before already is given by 0 times phi prime plus 1 times phi prime, which then gives under this new transformation that we just introduced, so the complex conjugate transpose with a tensor product with the new transformation V, giving us phi and phi double prime and psi double prime, so with the numbers lambda and mu that we just discussed before, so which is then lambda associated with 0 times 0 and mu with 1 times 1, which can also be written as the states so U, the complex conjugate transpose, and we see tensor again with the transformation V, and then we see the standard controlled knot operation applied to that state here. Okay, and we have our remaining qubit out here. So which is a unit vector, or as it is a unit vector, as follows from this one here, that psi and that lambda and mu are unit vectors, so the state is a unit vector and can be obtained from zero by a unitary transformation, W summarizing everything that we just applied before. Okay, so a general 1-qubit state psi can be constructed out of 3 1-qubit unitaries and a single controlled NOT gate acting on the standard state 0, 0. Just to summarize a couple of things. So for classical bits and quantum bits, we have some differences here. So the states of n classical qubits is given by, so let's say we have a number of n classical bits, not qubits, sorry. We have a number n of bits, and that we have a definite state. Here we have a superposition state, so also again we have n bits, but we have x possible states here. So each of these x states associated with a probability amplitude alpha sub x, subject to the normalization. So classical bits always have states. There is no superposition for classical bits, and qubits generally have states. For the reversible operations on states, we have permutations and unitary transformations. And we can, for classical bits, learn the state from bits, whereas for quantum bits, we cannot. To learn the state of a bits, for classical bits, we examine them. For quantum bits, we have to measure them. Okay, so for classical, we look at them. For quantum bits, we measure them. And the information acquired, if we look at the classical state, is the classical state itself. And here we get the final state, the definite state, with a probability associated with that state. So this is the probability amplitude. And the state after information acquired, so after we look at the system, is still x was before, but here for the quantum state, it's different. Now it is in the state x. Today's lecture, we will look a little more at circuit diagrams, the diagrams that we briefly discussed in the previous lecture and also in this lecture. It's just another way of representing quantum algorithms. So it's very common practice in quantum computer science to represent the action of a sequence of gates acting on n qubits by a circuit diagram, where the initial state appears on the left and the final state on the right. You will also see for a couple of APIs available, such as Qiskit from IBM, that's a very good example. They give you the possibility to construct circuits, so graphically, so with a graphical user interface. And a circuit diagram representing the action on a single qubit of a 1-qubit gate U is given by this circuit here. So we have an initial state psi, apply the gate U to it, and then we get the result U of psi. The wire, the thin line here, represents the subsequent history of the qubit, leading us to the final state. A circuit diagram representing the action on n qubits of a 1-qubit gate is given by U. So here we have the bar, the thick line, representing the subsequent history of the qubits. So the thick line just indicates we're operating on multiple qubits instead of 1 qubit, and the capital U indicates we're operating on these multiple qubit with a multi-qubit unitary, and the box represents the unitary transformations. One thing that I once more want to emphasize on is the sequence of gates. So here, when we evolve the state from the left to the right, we of course apply the gate V before we apply the gate U, which would read in bracket notation. So the sequence flipped here because here too we want to apply V to the state psi first, followed by U, which is a good. So all in all, this circuit diagram is a very handy way of representing a set of gates applied to many qubits instead of the lengthy formulae that we also saw before. As we said, we run from the left to the right. That's how we evolve. That's how time runs. And once more, a qubit is denoted by a single line, often called a quantum wire, represents a qubit which is not evolving, which is acted upon by I. So if we have a qubit where you don't see a gate and you just see a single line, then it doesn't mean we don't apply transformation. So we apply the identity transformation on it, so which means leave the qubit alone. Okay. So a particular unitary evolution is to be enacted on our qubit. Then we put a box with a symbol describing this unitary transformation along the quantum wire. So this is also no news for the Hadamard transformation. We saw that before. The Hadamard transformation is given by that matrix here. If we apply it to the zero state, then in the quantum circuit it looks like that. The resulting state, we already know that well, is given by 1 over square root of 2, 0 plus 1 if the input state is 0. And if we measure the system, so here is a different symbol for measurement, then this specific state up here will collapse with 50% probability in either 0 or 1. So based on that, we can already create some very nice circuits and little circuits that seem to be very different from, or that are very different from classical circuits. Which is that one that we already talked about. So we have double application of H. So we will see later on when it makes sense to do that, so to apply a transformation twice. And that, for example, makes sense if we one act on a superposition and then end up with a definite state again. So we create a superposition and then a controlled operation based on that superposition or on that superposition, and then we collapse the state again. So that's when it may make sense to do it. So applying it twice will leave us with the state 0 again, which is true for all valid quantum gates, right? So we want to make sure it's reversible. So now suppose we apply the Z operator after applying the Hadamard gate. So if we do that, right before the measurement, we see this state here with 1/2 probability of 0 and 1 over 2 probability of 1. So it's 50-50 that we measure 0 and 1. But then if we apply a Hadamard before performing a measurement, so for example in that circuit, so we have our Hadamard here taking this state here into 1 over square root of 2, 0 plus 1. We apply that one, which shifts the relative phase. Then we apply Hadamard again. We will definitely end up with the state 1 with 100% probability, right? So this is kind of peculiar. So applying an operation which didn't have an observable consequence after applying the Hadamard, after applying a second Hadamard, so resulted in a totally different configuration. And this demonstrates to use that is not just the magnitude of the amplitudes in the quantum state that matter. So for example, if A, alpha and beta here, if you look at that state, it's not only alpha and beta that matters. So what we say is that the phases of different configurations matters. So, okay. So remember we talked about global and relative phases before. Global phases don't matter. It's still the same physical state, but relative phases matter. And because of this phase, we see that the amplitudes can add in interesting ways that probabilities can't. And in this particular example, we see that when we feed in our state 1 over square root of 2, 0 plus 1 into the Hadamard, then the amplitudes to go to the 0 configuration constructively add up, but the amplitudes to the 1 configuration destructively subtract and become 0. Interesting, right? So by changing the phase, the relative phase here, so by minus, we observe the inverse, so the reverse. We observe that for 1, they constructively add up, and for 0, they destructively subtract. There's not only interference, which is going to make a quantum computer special, because we can imagine building a machine which uses classical waves, like the waves on a pond, which do also interfere to construct a computer. So in theory, this is possible, but it's not just a classical wave machine. So again, we end up with a quiz for today, where you can please consider a couple of different states in this first question and see what happens if we measure the system and try to conclude the answers. Thank you very much for listening in, and we'll talk soon about quantum algorithms. Thank you.